All right, in this lesson we return to this idea of particle motion, and this should be super familiar because we studied this for an entire module when we were working on derivatives. Here we're going to see how integrals fit into the picture. This is also exciting because we can actually do, this is an FRQ from a previous AP Calc exam, and we can actually do this whole question now that we know about integrals. So we're going to start by reviewing a little bit of the vocabulary, and notice the second page of your notes here is essentially a glossary, so it helps you decipher what all these words mean. Most of them are familiar, things like speed and velocity, but some are new, such as displacement. So we're going to put these terms in context that is hopefully familiar to everybody. We're going to imagine we're just driving a car, and we need a point of reference to talk about all this stuff. So we're imagine we're starting at our house and we're getting in our car and we're driving away, right? So our position is just, really it's the distance from home, right? So how far are we from home? How far do we drive? And that's usually written as either x of t or s of t. Your velocity is basically what your speedometer says. So the little needle points at 20 miles per hour. That is your velocity. The only catch is this can be positive or negative, depending on direction. Right? So a positive velocity would be, so we think of positive velocity as moving to the right, or negative as moving to the left, is how we saw it before, or we can think of it as just moving towards home or away from home in this example. And then acceleration is sort of the least tangible one. It's the rate of change of velocity, right? So just like velocity is the rate of change of position, acceleration would be how fast is your speedometer changing. Right, and that tells you, am I speeding up or slowing down? If my speedometer increases from 20 to 30, that's acceleration. So those are our reviews, and then these have names as well, right? So velocity we usually call v of t, and acceleration we usually call a of t, right? So that should all be familiar. That is a review, and then those definitions are also in your little glossary. And then remember, we have derivatives, which give us the rate of change of a function at a particular time, right? And we have integrals, which gives us the total change in a function at a particular, over a particular time interval. Okay, so the relationship here then is taking a derivative sort of moves me down a level in this chart, right? So the derivative of position is velocity, and then the derivative of velocity is acceleration. And then if I go the other way, I'm integrating, right? So this will be the integral of acceleration with respect to time will give me velocity, and then the integral of position, of velocity with respect to time rather, will give me position. Okay. So that's how we navigate these three functions with our derivatives and integrals. I'm being a little loose with the notation here. We'll continue to work on that, but here I want you to just focus on the relationships. Okay. So now we have enough information here to tackle this FRQ. So make sure you've read the whole thing, both like the little stem here and questions A through D. Note that we have velocity given here, and then I would also annotate that velocity is the graph, right? So the graph is the function that we're given. That's not always the same thing. Sometimes we might be given different graphs of different functions. And then we are looking for acceleration in part A. Okay, so that's pretty easy. Acceleration, right? It's asking us for acceleration at time 3. Well, that's just the derivative of velocity at 3. And to do that, I can either take a derivative by hand, right? Or I can just use my Math Aid button. So here's a trick when we're working with the same function over and over, right? I'm going to type it into the grapher in my calculator. And then if I want the derivative, I can do Math 8 d dx, we're looking at the 3 is my value. And then here, instead of retyping that function, I can do variables, y variables, function, and then here's my y1. So that's going to plug in the function that I typed in for y1. And then I go ahead and calculate that, and that's my acceleration. And you could have done that by hand. It's a trig derivative, but it's not that hard. We would use chain rule here, right? And we will keep the sign, and we're going to give 3 decimal places. Rounding doesn't matter. You can round up or down. And then we're also going to give a unit if it has one. But notice there's no units for v and t in the text, so we don't have to worry about units for this particular question. So we're done. So that's a whole point on my FRQ right there. And we'll move on to part B. Part B is find the total distance traveled by the particle from time t0 to time t3. Let's do that one last, actually. We'll do part C next. Part C is the easiest one that we have remaining. So part C is asking for position at time 3. So position we'll call x of 3. And x of 3, so we're given velocity. So I need to integrate velocity to get to position. So notice I have x of 0. X of 0 is 5. So what I need to do is I need to write an integral that gets me from that x of 0 to 3. And then I need to add in x of 0, right? Because the total change in position plus my original position is what is going to get me to my position at 3, right? And notice the 0 matches this 0 here. Okay. So that's my integral, and again, I can just integrate this on my calculator. So we'll do math 9 now. And we're integrating from 0 to 3. And then y1 is our v of t, right? dx. And then we're going to just add in, we're just going to add in that original initial condition, which was 5. Good, 5.77. That is our position, x of 3. And I want you to focus on the ideas here more than the scoring. But just for the record, this would be 3 whole points in this FRQ, just for writing it just like this, right? So you get 1 point for setting up the integral, 1 point for using your initial condition, and then 1 point for the result. Now, part D here, we want the time when the particle is furthest to the right. So this is really an absolute maximum position, right? And notice we have the derivative of position. So we want an absolute maximum position. We have the derivative already. So our maximum has to be either at 0 or square root of 5 pi, or at one of the zeros. And particularly our zeros, we want positive to negative zeros of our derivative, right? So positive to negative here, positive to negative here. So here's where we're going to make a table. So we're going to make a t, x of t table. And we know we're going to consider 0, square root of 5 pi. And then my other two zeros, so these zeros that I circled in the graph, here's where you need some unit circle knowledge from last year for this particular problem. So square root of pi is this 0, because sine is 0 for every multiple of pi. And then square root of 3 pi for this one, because this is square root of 2 pi here, but that's not the sign change that we're looking for. So those are our 3 zeros. You could also find the zeros using the zero function on your calculator if your trig knowledge is a little bit weaker. So square root of pi, square root of 3 pi. And then, first one was given to us as 5. The rest we can integrate, just like we did before. So what I can do is I can just edit my previous integral. So we're going to start with square root of pi as my upper bound. Oops. And there's my first value, 5.895. And then I'll repeat for the rest of my values. So notice they're all pretty close here, but my rightmost position is here. T equals square root of pi. So here's my answer, here's my reason. And scoring wise, you get a point for identifying your zeros, a point for your reason, then a point for your result. So that's 3 points there. And then part B is the newest thing. So the total distance traveled by the particle from 0 to 3. So that is related to these ideas here, right? So displacement, to use our car example, how far do I end up from home? Whereas distance is how many miles did you drive? So distance doesn't care if you're driving towards home or away from home. Displacement does, right? So that's why this one's a little bit harder. So notice I take the absolute value of my integral here. That's what those bars mean. Oops. And the reason is, notice I have intervals where I'm moving right and left, right? If I don't take the absolute value, those leftward moving intervals are subtracting from my total, right? I just want the total distance that I drive. Left should be positive as well. So for part B, I'm going to take the integral from 0 to 3, because the question is asking about the interval from 0 to 3, of the absolute value of velocity with respect to time. And I don't need that 5 this time, that x of 0 that I included in the others, because I just care about how far I've driven, not where I end up. So I can take the integral that I was taking before, get rid of the 5, change this upper bound to 3, and then in here I need to insert the absolute value, and that's math, numbers, ABS. Oops. And we want our y1 to be inside there, obviously. Your calculator has to do a little bit of thinking there, but there is our total distance, 1.072. So that is our entire FRQ. This is, again, a 2-pointer, one for just this, so demonstrate you know what displacement is, or total distance is, and then one for your result. So that, I believe, is our first full-length FRQ of the year. Notice it puts together several different concepts from throughout the course. And notice, even if I didn't know how to answer a specific part, so say I didn't know how to do part D, that was the most involved one, none of the other parts rely on knowledge from part D. So we could have done part of this even if we got stuck on a particular question.